Hey there, this is Rez and I've been a Houdini Pro for the last 4 years, and let me tell you, Pyro is the king of fire and smoke simulations. Yes, there are other software out there like Divergence or other plugins for Cinema 4D and add-ons for Blender, and while those are cute and you can impress your mom by using them, there's nothing like the real deal. There's no substitute for Houdini. The amount of control and complexity you can get in Houdini is unmatched. In this course, I'll show you how to use Pyro to achieve amazing results with simple setups. By the end, you'll have the skills to build any kind of fire effect you can imagine. So let's get started. Let's create a geo container and we'll step inside and let's drop down the Pyro solver. So if we look at the properties here, we can see that we really have a lot of tabs with a lot of different settings. So there's really a lot of options for us, which is a good thing because we can get very specific with our simulations, but this can be quite overwhelming at start. So first, let's only focus on the sourcing tab over here. This tab is the most important tab because without sources, we can't have anything. Pyrosolver by default doesn't know how to make fire or smoke out of nothing, so we have to base it on some existing volume. So let's create a simple sphere. I'll drop down a sphere. Let's set this to be a polygon and we'll just increase the frequency here. And let's also increase the uniform scale. So we'll make this bigger. Let's try a value of 3. Now, right off the bat, scale is very important with Pyro simulations and simulations in general. And we'll get more into this later, but for now, let's just keep the uniform scale at 3 and this will be fine. So let's turn this into a fog volume. So from our sphere, we can drop a VDB from polygons and we'll turn on our fog VDB option here and uncheck the distance VDB, and now we have some smoke. Now really the volume that we created is called density, as it says over here, and whenever I'm talking about smoke, I'm really talking about density. And we're going to be using a lot of the knowledge and techniques we explored in the Intro to Volumes course, so we need to know how to create and manipulate volumes outside of the Pyrosolver. The Intro to Volumes course is also free and available on our website, voxsite.com. So let's add a null from here and keep things organized, and let's rename this to source. And now we can plug this directly in the first input of our Pyrosolver. And if we look at this now, we no longer have this error on our Pyrosolver. And now if we press play, we can see something happening, but it's not really looking like any kind of explosion or any kind of smoke simulation. We can see that the smoke gets thicker as the simulation progresses, and this is because so far this is really all that we are doing. We're just adding the density values we have in our source each frame. So if we have density values of 1 from our source in the first frame of our simulation, we'll have a value of 1 for our density, and on the next frame we'll keep adding this 1 value. So on frame 2 we'll have density values of 2 and so on. So this is why as we progress our smoke gets thicker, because we are continuously pumping density values into it. So let's add some motion to this and we can now introduce the shape tab. We have quite a few settings here and we'll explore all of these gradually. We have by default the buoyancy option here turned on. I will turn this off for now because this is going to look for a temperature field in order for this to work, and we don't have this, we only have the density, so let's not worry about this for now. Let's instead turn on the turbulence option, and we can also expand this window here and see what options we have for the turbulence. This option, turbulence, will add noise to our simulation, and as we already know, noise is pretty much the heart of almost all Houdini simulations. So we'll reset the simulation, and if we press play, we can see that nothing happens. And this is because by default, Houdini likes to map the threshold field of the turbulence to this temperature field, which again, we do not have yet. So let's just set this to our density for now because we only have the density. The threshold range here in most cases will be fine with these default settings. More importantly, and this will come in later, will be the control field. So we'll talk about this more later. Let's reset our simulation, and if we press play now, we can see now that this is starting to look like an actual smoke simulation. Now by default the density is disappearing a little bit too fast. And to make it less longer, we can go up here, we can go in the Fields tab, and we will just decrease this dissipation option here. Let's just set this to a lower value, maybe 0.02. And we'll talk more about the fields tab later, but for now we're just interested in this dissipation option here. So again, this controls how fast the smoke disappears. And if I reset, we can see now that the smoke has more time to evolve and create nice, interesting features. And if we go back to our shape tab inside the turbulence tab, most of these settings will be pretty self-explanatory, like the usual noise settings. The turbulence value here determines the amount. So if I increase this, we are going to have a lot more turbulence. Like this. The swirl size determines how big our noise is, so let's set this lower, the amplitude. This turbulence is basically the amplitude, and this is the scale, so if I increase the swirl size, we'll have, as the name suggests, bigger swirls, like so, and we can increase the roughness, maybe to have more features, but keep the large swirls. We also have pulse length, which animates our noise, so if I decrease this, our noise will evolve faster, and we'll have a lot more of a chaotic look. Maybe we can pair this with a lower swirl size, and a lot of these settings you'll just have to play around with until you get the look that you want, and you're going to have to keep resetting the simulation and try out different values. So at its core, this is the most simple setup that we can have right now, and we can slowly build on top of this. So when we get down to it, really the main things that drive any pyro simulation is going to be the sourcing and the shaping. So let's look at the shape for now, and we can really play with a lot of these settings here for our wind, disturbance, turbulence, and so on. But we're not really limited to only these parameters here. In fact, if we step inside the Microsolver by double-clicking, here Houdini exposes for us a few different outputs where we can wire various DOP level nodes. So in this space, we are actually inside the dynamics context. So if I press tab, we have access to all of our DOP level nodes. And we can see what happened when I double-click the Microsolver. We actually went inside a DOP net and inside the forces subnetwork, which is this space over here. Houdini does this for us so we don't have to go inside the actual DOP net. So if I click on this, we can see that we have this huge network with over 5,000 nodes, and this is actually where our Microsolver lives. Houdini only exposes for us only the parameters that we need from all of these various nodes in order to shape our smoke. So when we go back to our Microsolver at the sublevel over here, all of these settings that we have for all of our different tabs are going to be tied to values from all of the different nodes inside the actual DOPnet. And for the most part, all of these settings here are enough for maybe 90% of all cases. But in the case that we need to add any extra stuff, we can just double click this Microsolver, and in this space here we can wire additional nodes that will tie back to our DOPnet. And we have a little guide over here that says that we can wire Microsolvers to forces output to apply forces on the pyrosim or any other dynamic effects. So if we want, we can do a gas turbulence over here. So I will place this down and I will wire this in my force output. And if I go up at the top level by pressing U, I will turn off the turbulence so we don't have anything turned on here in the shape tab. And if I press play, we're still going to have noise affecting our smoke. So this is driven by this gas turbulence over here. So when we talk about shaping, we are really talking about Microsolvers. So this is what all of these different tabs do. They are just tied to different Microsolvers. And if we step back inside, if I press tab and I go to, let's find Microsolvers, we can see here that there's really a lot of them. And obviously we only really need to know a few of these. But all of this is to say that in case we need anything extra that it's not on the Microsolver, we can just add it ourselves in this space when we double click the Microsolver to step inside the actual DOPnet. So very rarely you will have to go inside this DOPnet over here and do changes here. We can have a lot of control directly on our Microsolver, and for anything extra we'll step inside and we'll use these three outputs that Houdini exposes for us. So again, when it comes to shaping, we are talking about Microsolvers. So this will be your gas turbulence, disturbance, viscosity, and we'll slowly start introducing more of them as we dive deeper. If you want to see how Pyro is used in real-world projects and how to implement the techniques I'm about to show, you can check out my premium courses on voxite.com. These are full in-depth courses covering many different aspects of VFX, including shot assembly, rendering, and even compositing. So let's go ahead and let's just get rid of this gas turbulence. And if I go up, I'm going to keep all of these microsolvers off so we can focus only on the sourcing tab here. Now by default, when we place down a pyrosolver node, it adds a lot of sources here, but we only really have density. So for now, I will just get rid of any other source and just focus on our density. So let's examine what happens here. We have a source volume and a target field. Now our source volume is grabbing the name that we specify in our sources here. So in our VDB from polygons, we set our VDB name to density. So this is what our source volume will look for. This is the name that it will look for. And now the target field is the built-in name that the pyrosolver recognizes internally to drive our smoke. So right now it's a little bit confusing because we have the same density name for both our source volume and our target field. But for example, if I were to go back in the VDB from polygons and I would change this name here to source, all right, and we can check that our name here is source. We can go back to our pyrosolver. We can see that nothing happens now because we no longer have this here. So we have to update our source volume name to source. All right, so now if I press play, we see that everything is working as it should. So for our source volume, we can use any name we want, but the target field has to be named density in order for Pyro to know what to do with it. So back in our graph, we can see that the source volume goes in the target field, and the name of our source volume can be anything, but the target field name can't change. So here are some of the target field names. We have density, temperature, divergence, val, flame, and we have a few more, but these are the ones that we want to focus on right now. And usually you will find that the source volumes have the same names. So density gets sourced in the density target field, temperature goes into temperature, and so on. But for example, for the velocity field, sometimes you will find the name used vel, and sometimes you will also just simply find the name v. So v can also be the name of the source volume for the velocity target field, and we can see that burn gets sourced into the target field flame. And this is really because a lot of the pre-made Houdini setups use this naming convention, so we'll explore those later. But what I want you to remember here is that the target field name has to be one of these built-in ones. And again, let's just focus on the density for now. So let's go back in Houdini, and for our density, we'll set the name here back to density for our fog VDB, and let's also change the source volume name here to density. And let's take a look at some of the other settings. So for our operation here, this is set to add. We have a few operations here which we will cover in a bit, but the default add operation will simply add density each frame on top of the density that we already have. So this is why the smoke thickens. And this option here, which says scalar, can specify whether we are sourcing in a scalar or a vector volume. So we know this from intro to volumes that if we are storing a value that has only one dimension, which is the case for density, it will be a scalar. And if we want to source in velocities, we will have to work with a vector signature here. So this is what this option is. And the source scale sort of acts as a multiplier. So if I set this to 0.1, now we will only use 10% of our source values that we are going to keep adding into our simulation. And if I set this to a bigger value, so a value of 10, now we can see that we add really a lot of density. It's a little bit hard to tell because we don't have any motion, but this is essentially what this source scale is more or less. And again, we'll talk more about this in a second. And to better explain all of these options, I want to introduce a velocity source. And for this, we are going to create a velocity field. And again, we go more in depth on how to create velocity volumes in the Intro to Volume series. Now let's get rid of this annoying blue background. I'll press D and we can go to the background here. I'll change this to dark so we can preview our volumes better. And also here in the guides tab, I have the draw time FPS on so we can see the frames per second we are getting when we play our simulation, so we can check sort of like the efficiency of our setups. And in this geometry information tab, this is always on, so we can also see the amount of voxels we have, and this also displays the geometry point number and primitive number. All right, so let's close this, and I'll also close the parameters over here. I'll close all these tabs so we can only have our network view. and I'll just press P so we can bring back our parameters. And this is really my preferred way of working, just so we have more real estate on our screen. So again, all we have for now is a sphere that's turned into a fog volume, which we are sourcing in as our density field. And in the shape tab, I turn everything off. And in the sourcing tab, we only have this source volume density, which is being sourced in the target field density. So let's create a velocity field. And the reason I want to bring up the velocity right away is because by just sourcing in density and velocity, we can really cover a lot of different cases without having to rely on microsolvers. So too often I find that people right away just start adding microsolvers to control the simulation. And when you want to achieve a specific motion, like the smoke going along a curve or wrapping around geometry, a lot of times it's easier to just directly tell the smoke how we want it to move with a velocity field. Of course, on top of that, we'll still add microsolvers, but with velocity fields, we can maybe get 70% of the way there. And this again is why it's important to know how to manipulate volumes outside of the pyrosolver. Anyway, let's drop down a box. And let's look at our pyrosolver, and I'll press E on our box, press enter so we can have our handles, and I'll just increase the size here, and I'll just make this box big enough to sort of contain our simulation. So this is what we can base our volume velocity on, and this again will go back to our Intro to Pyro course, where we created a velocity field. So let's drop down a VDB, and I will name this V. So it's very important that we keep track of this name. The class here will be fog volume, as it is already, and the type will be vector float. And we want to use vector type displacement velocity acceleration. We don't need any background values for now, and we'll leave the voxel size at 0.1 for now. So now we can do a VDB activate, and I will place the box as the second input here, and let's set this to reference. All right, so now we can see our volume. And from here, we can simply drop down a volume VOP. And inside this volume VOP for now, let's step inside and let's just create a simple noise. So let's use a curl noise, and let's use the 4D signature, which means that our noise will also evolve over time. So from our position, we will do a vector to vector 4. Let's place the time as our second input here for fval4. And from here, let's do a curl noise. We will set the noise type here, let's use simplex, and we don't actually need the density here because we will do a bind export directly from our curl noise. Let's export this to our V volume that we created. So the name here is just simply V, and let's set this to 3 floats. So just by doing this, we already have a velocity field. So if we go up, let's bring this up. So I will hold down Shift, and with click, we can drag everything up. I'll do a null from here, and let's rename this to V_source. And we can be a little bit more specific with our density here, and let's rename this to density source. All right, so now to bring this in our pyrosolver, we can merge these two. So let's do a merge from our density and place the velocity volume, so our V volume, inside this merge. All right, and now in our pyrosolver, we can see that even though we have sourced in both of these volumes, we are only seeing our density source. So let's add in our velocity, and I'll hit this plus to add another source. Let's set the source volume here to V. So again, this is the name that we gave our velocity volume, this V. And we want to source this in the target field vel. All right, so this is the name that can't change. And we can go back to our graph, and we can see that we have this target field vel here. And the source volume can be either vel, and in this case, we are using just the simple letter V. All right, so let's go back, and for operation, we'll keep this as add, and let's not forget to set this to a vector type because we are dealing with velocities. So if we press play on our simulation, we can start to see that this is kind of mimicking the result that we had from our Turbulence microsolver, but we don't have any, in the shape that we don't have any microsolvers acting on the simulation. This is straight up from the velocity field. All right, so let's go back to sourcing and let's press play. simulate a few more frames. So this is the result that we get. So now we can go back to our curl noise and we can play around with the settings here. So I can maybe reduce the frequency if I want larger swirl size. And we can also increase the amplitude or roughness and play around with all of the settings. So if I reset the simulation, we can now see our new results. So now we have a lot more bigger swirls and smoother noise in general. And we can kind of clearly see the shape of our curl noise when the simulation progresses. So in fact, we can go up, and from my volume source, in order to preview this better, we can do a volume slice from here. Let's plug this inside a volume trail and let's point the volume to the second input as well. And if I look at the volume trail here, we can clearly see the shape of our noise. And when we look at our simulation, we can kind of see the way that the simulation behaves matches our pattern in the noise. So it's really cool that we can anticipate how our simulation will look without actually simulating anything, just from this volume trail node. Now, one of the problems that happens here is because this is such a huge volume, we can see that our simulation is much slower. So if I press play, we have roughly 3 frames per second here. Whereas if I only had the Microsolver, so if I turn off the velocity, let's reset the simulation. And if I go to the shape tab and turn back my turbulence and press play, we can see that we are running on 6 frames per second. So let's maybe just increase some of the settings here. I'll increase the turbulence and swirl size and I'll press play. So we can see that this is slightly faster for the most part. And in fact, this is still pretty slow. Let's maybe not source in the velocity at all. So if I hold down Y and cut this wire and reset, all right, now we can see that we are running at roughly 15 frames per second. So this is way faster with the Microsolvers. And the reason this is happening is because if we look at our volume source, since this is a rather big container and we have a lot of voxels here, we can see that we are working with roughly 2 million voxels. This is also evaluating every frame because our noise is moving. So if I just preview this result of the volume source, if I just preview this, we can see that this is slow as well. So if this is slow outside of our Pyro solver, it's definitely going to slow things down inside the Pyro solver as well. And this is often a very useful debugging technique. Always remember that if your sources are slow on playback, your simulation is probably going to be slow as well. So you always want to optimize things outside of the simulation as much as possible. So what we can do to optimize things here is we can simply increase the voxel size on our VDB. So from 0.1, let's go to 0.5. And if I just play the result of this velocity volume, we can see now that we have 24 frames per second. So now if I source this back in, let's plug this back in our merge, go to the Pyro solver and let's turn on velocity source. And we will go to the shape tab and let's disable turbulence back so we don't have any Microsolvers. If I press play now, we see we are running on roughly 10 FPS. It's obviously going to slow down as the simulation progresses, but now we can see that it's much faster. And we can also see that for the most part, we retain a lot of the details from our noise. So in fact, we didn't need this very low voxel size on our velocity volume of 0.1. We really only need high resolution on our velocity volumes when we want to get super specific with the details that we get. So when we want extra sharp features directly from our velocity field, then it's worth decreasing the voxel size here. But for the most part, for velocity volumes such as this, we don't really need a super high resolution. So in fact, I can probably set this voxel size to 1. So now it's going to be even faster. And we can see that maybe the result of the simulation is a little bit too smooth, so we don't have all of those nice features, but for the most part we retain the motion that we had originally. And now if we want to bring back some of the details and smaller features, we can just use Microsolvers on top of our velocity. So here in our Pyro solver, if I just turn back on the turbulence, let's keep this at 0.5, and because I want smaller features, let's maybe just decrease the swirl size and make the scale of this noise rather small. So let's maybe just duplicate this Pyro solver. I'll reset my timeline. I'll hold down Alt to duplicate the Pyro solver, and for the second copy, I'll do a transform and just move this over to the side so we can compare the two different results. and let's go ahead and merge these two. All right, and for our first one, we'll keep the turbulence on, and for our second one, let's turn this off, so it's just using our velocity field for advection. So it just has the velocity field. And if I press play now, let's take a look. We can already see right from the start that we have a little bit more features in this one, where we have the Turbulence microsolvers on top. So if I press play, this is the result that we get. So we have all of these small features on top of our original motion. Okay, so this is a very efficient way of working. The strategy often is that we get our general direction from our velocity field, and then on top of this, we add features with the microsolvers. This way we get nice fast results, and we don't have to guess as much how our smoke is going to look and behave. And now really from here, the sky is the limit. We can see how far we got with just adding a simple curl noise inside a volume VOP for this velocity field. But obviously we can get a lot more advanced, and we know this again from intro to volumes, that we can really control this velocity field and push it in any direction that we want. So let's start to introduce a few more layers inside our velocity field. So I'll go ahead and get rid of this copy, and let's get rid of the merge and focus on our main setup. And also in the shape tab, I will disable the turbulence, and let's make sure that we have no microsolvers affecting our simulation, so we can focus on our sourcing. And for our velocity field, let's go back, let's preview our volume trail, and let's go back in our volume VOP. And if I want to add a simple wind to this velocity field, we can simply drop down a constant. So let's drop this here. I will make this a 3 floats. Let's make this wind point straight up. So let's do 0, 1, and 0. And we can simply add this to our bind export for our V here. So let's go ahead and add this. And we can kind of see the result here. Let's maybe also do a multiply constant after, so we can also scale down this vector maybe back a bit. So I will just reduce the multiplier here. So we can see that as I reduce the strength of our wind, we get back more of our noise motion that we had originally. So now from here, let's go back and let's see what we get. And if I play the simulation, and we can see now that we introduced a simple wind. So maybe this is a little bit too strong. I can go back here and I can reduce this wind vector, so I can just scale down with our multiply constant. And if I reset the simulation, now it's still going to point up slightly. Maybe now the noise needs adjusting, so I can go to the curl noise. I can reduce the amplitude, so we can start playing around. And hopefully we can see that just with a few nodes here, we really start to have a lot of control. And for example, I can simply change the direction of the wind by changing our initial vector. So here I can do 1, 0, and 0. So now our wind should be pushing off to the side. So this is just to give you some examples. One of the things that I want to do here is maybe introduce some noise on our density source. This is kind of bothering me for a while now. So let's go back up, and after our VDB from polygons over here, let's go ahead and we can use volume VOPs to introduce some noise and breakup as well. But let's just use a volume noise fog, so it's just a little bit faster. I'll set the operation to multiply. Let's also enable ramp, remap ramp, and I'll just move this handle here over to the right, so we can see we start to have some nice breakup. And also let's turn on animation, and if I play this back, this is going to be our source. Again, wherever you can add noise and breakup in your sources, this is going to translate to your simulations to get more interesting features and details. And generally, it's recommended that you add noise as much as possible. So let's go back to our Pyro solver and let's press play. So now with the noise from our source and the noise from our velocity field, we start to have a lot of nice, interesting features. We have our wind from left to right, and we can control this direction. So all of this is again achieved only through these two sources, which is really cool. In fact, let's go ahead and recreate the velocity field based on a curve that we did in the Intro to Volumes course. So let's go ahead and I'll disconnect this wind velocity field. I'll just drag this over to the side, and let's go ahead and drop down a curve. So we'll just go ahead and recreate the setup that we had. So let's use a NURBS curve for this. And I also maybe want to preview the sphere geometry to have as a reference. Let's turn back on the grid. I'll press enter in the viewport to go into draw mode, and maybe I'll press spacebar 4 to go in the right orthographic view, and I'll just add a few points here and draw a simple curve. 4 points should be enough. I'll press F to go into edit mode, and now I can further adjust these points a bit. I don't want to spend too much time on this. Let's also go back with spacebar 1 in our viewport, and I also maybe want to introduce some 3D dimensionality to this, so it's not completely straight on a plane. And this will be fine. Let's also, this is a NURBS curve, so we'll have to convert this to geometry with a resample node. So let's drop this here, which converts it into points that are usable. So let's maybe just increase this length here. We don't really need as many points. It will only slow down our velocity field calculations probably. And this should be fine. Let's go ahead and turn this into actual geometry, so not a curve. We'll use a sweep from here, set the surface shape to round tube, and I'll just increase the radius. And we have to make sure that our radius is large enough to contain our entire velocity field volume. So let's make this nice and big, maybe something like this. If you press Shift W to view the wireframe, I might also want to increase the columns. And we have to close this off in order to turn it into a volume. So for end caps here, let's just use grid, and this will be fine. We can always go back. Let's maybe use a radius of 5 in this case, turn off the point display, and we'll have to convert this into a fog volume first. So let's do a VDB from polygons. So again, we don't really need super high resolutions on our velocity fields. Let's use 0.5 to start with, and we will do a fog VDB, which gives us our density field. And in fact, let's go ahead and set the name here to V as well. And now we have to convert this to a vector volume. So let's do a VDB convert, and I'll set the convert here to VDB. And for VDB type, let's use vector float, and the rest of the settings should be kept the same. Okay, so now if I go to the information tab, we have a volume called V, and this is a vector3 volume. Perfect. So we can use a volume VOB from here to give this our initial direction, and we will have to reference our curve geometry. Let's go ahead and make some room over here. And from our curve geometry, we will need to store the direction of our points as they go along the curve. So I'll turn on the point display here, and we can use a polyframe for this. So let's drop down a polyframe node. I'll turn off the normal, and for our tangent name, I'll set this to N, just so we can preview this as our normal. So if I turn on the normal display, we have our normal here, but it's scaled a little bit too low. I can press D on the viewport, and I can go to the guides here, and I can just increase how our normal vector is being displayed. So I'll just increase this, and now we can see we have this direction along our curve. We can also see now that the vectors are pointing in the opposite direction of what we want, but we can control this inside the volume VOP. Anyway, from here, we can now reference our curve with the normal information inside the volume VOP. So I will place this as the second input. And let's go ahead here in the volume VOP, get rid of the density export from our second input, which again will be our curve. Let's use a PC open so we can grab the attributes from our geometry. We will want to base this on our position, and let's make sure that our search radius is big enough for each voxel to be able to find a point on the curve. So I'll just make this radius. We know from our, if I go up, we know from our sweep node that we use a radius of 5. So this radius here, the search radius, should be at least 5 as well. Just to be safe, I'll set this to 6. So we have to specify what attribute we want to grab. So we'll use a PC filter for this, and we want to grab our N attribute, which is again the direction along the curve. And we will simply do a bind export and export this to our V velocity volumes. So here I'll set the name to V, and let's set the type to 3 floats. And here it is. So in order to preview our velocities better, let's go ahead and in fact, I'll just copy the null with this setup. I'll paste it over here so we can hook this to our volume. Now this is using the volume slice to draw our trails. Let's go ahead and disable the point display, and this is what we get. We could use a different plane, so we could set this plane for the volume slice to maybe ZX, and this makes a little bit more sense. So it's cutting our volume along the z and x plane. So this is the result that we get. And like I mentioned earlier, our vector is pointing in the wrong direction. So to reverse the direction, we can simply add a negate after we grab our attribute here. So let's drop down a negate to reverse the direction, and we can see now that it's pointing where we want it. So if I go up and if I source our new velocity volume, let's merge this with our density. Let's go to our Pyro solver and let's leave everything as it is and let's see what we get. So let's press play, and we can also preview our curve at the same time, just so we know where our curve is in 3D space. So let's go ahead and keep simulating. This is the result that we get. So we see that in the beginning, we get the result that we want, which is the volume going along the curve. But after a while, it gets pushed so further out that it escapes this curve field, and our smoke just kind of wanders off and starts doing its own thing. So this is probably not what we want, but our velocity field is working. And now to further control how our smoke behaves, we can start talking about the operation options that we have over here. So with this add operation, we are going to continuously add on top of what we have already, which is fine for density. And this is mostly because as the simulation progresses, the density that we add is getting pushed away from our source. So in this case, it's fine that we keep adding density, otherwise we wouldn't get a continuous emission. But when it comes to velocity, this add operation accumulates speed over time, since each frame we are adding vectors on top of each other. So let's head over to Photoshop real quick, and let's say that this grid is a cross-section of our velocity field. And let's say that in our velocity field we have vectors that look something like this. So let's maybe just draw something like a curve. So maybe it goes something like this. And let's say that our smoke is maybe over here. So it reached this destination. So let's say that when our smoke is on this voxel, it's going to pick up this vector from our velocity field and it's going to move in this direction like so. And then when our smoke reaches this other vector, this new vector from this voxel, it's going to grab this direction, but it's going to carry over the length from this vector. So the new vector that will get applied is going to look actually something like this. So our smoke is going to be pushed further out than what we want. And the same thing is going to happen when it gets to this vector. We are going to carry over the length of the other vector. So the smoke is going to be pushed even further out every time we are adding new vector values. So we have to keep in mind that this add here has this accumulating nature to it. And this is why we start off pretty slow and then very fast we go to a very high speed. And in fact, we are going to push the smoke too much further out that it's not going to pick up any vectors because our velocity field only exists in this domain. And this is fine when we are doing burst or explosion type of effects because we're only sourcing in velocities for a few frames usually. Or we can tie the velocities to particles that disappear over time, again after a few frames. So in that case, we might want to use this add operation, and we'll get to some examples later. But when we are working with these large type of containers for the velocity fields, we run into this problem where the velocity starts slow and then really quickly turns super fast and we can no longer control it. Now, if we set this operation here to maximum, we still add the velocity to our simulation, but we clamp the speed. And when we are actually working with vectors over here, let's turn on this use vector length because we are sourcing in a vector type volume. So if I reset the simulation and press play, we can see that the smoke is kind of moving, but now we are lacking some speed. So we might as well go back to our volume VOP and let's create some controls here. Let's multiply our volume. We'll do a multiply after the negate and we'll promote our second input over here. And let's rename this to direction strength. And we can also, while we are here, let's also introduce some noise. So let's do a vector to vector 4 from the position. We'll place the time as our fourth value and let's use an anti-alias flow noise this time. Let's also set this to a 3D noise and we will add this after we do our multiply. So let's do an add here and we will add this noise. And we might as well right click, go to options here, and let's promote input parameters. And now if I go up, let's maybe preview our volume trail instead, and we can see our noise. Let's maybe instead of this volume slice, we can just scatter points inside this sweep geometry. So over to the side, I will do a points from volume, and we don't need as many points. Let's just scatter a few, and I will place this as the first input of this volume trail. So now if we look at our volume trail result, we have this 3D representation of our velocity field. Maybe we don't need as many points. Let's do something like this. Okay, so let's go back here and let's increase the direction strength. So as I increase this, we see we bring back our direction. So let's give this a value of 3, and then we also probably need to increase the amplitude of our noise. Let's go back to our Pyro solver and let's press play. Okay, so now we see that we are indeed following the curve. Let's also template the curve geometry. So we are now following the curve, but we have this constant speed. So what happens when we set the operation here to maximum, the values get clamped for our vectors. So we are no longer accumulating our vectors, but instead we are adding in the new direction that we are reading, and we are clamping the speed based on the length of our vector from the voxel that it's sampling from. So this is why we will have a constant speed, but we are still updating the direction based on our velocity field. And this is a little bit easier to control. So we can see now that we are starting to follow the curve a little bit more accurately. So this is kind of the result that we are after. We can see that some of this smoke is still escaping, and we can probably do some tweaks to our velocity field to control this better. And this is what the maximum operation will do for us. Now, typically the maximum operation is not used in sourcing in velocity values. You will more often find this used in scalar fields, so with density or temperature, and again we'll get into more examples in a bit. But sometimes it can work with velocities as well, as we can see here. Now, if we set this operation to pull, we'll have a similar thing happening as with our maximum, in the sense that we are not accumulating the speed, but the velocities will blend over time to match the values from our field, as opposed to straight up adding them. And this is what this acceleration and deceleration strength means over here. And also when we have this pull operation and we are working with vectors, we have to turn on the direction strength. So what this pull means is when our smoke will move slow, it's going to look at our velocity field and accelerate the values to match the values from our field. And when the smoke picks up speed and moves faster, they're going to slowly decelerate. And when the smoke decelerates, it's allowed to move freely. And this will give us a nice, natural, smooth motion. So typically for these options, we want the smoke to accelerate faster towards the value. So I'll use a value of 10 here. And for deceleration strength, I'll leave this at 1. So let's see the result that we get now. We can see that it moves towards the values in our field rather fast. And then if it reaches a big enough speed, it's going to start to decelerate, so it's no longer going to grab the values and it's allowed to move freely. So this is kind of what's happening here, and we can see that for the most part we have a pretty nice, natural, smooth motion. So let's play this back again in real time. I'm pretty okay with this result. We can see that again, it's not really adhering to our curve that tightly. And this again will require some finessing with the settings here and also our velocity field itself. But typically pull is what we like to use when we're doing a lot of magical effects, because you have these nice natural movements. Right, and finally, sometimes we can use copy here as well. So if I set this to copy and I reset, what's going to happen is copy will simply read the values from our velocity field and replace whatever values we had previously. So it has an overriding nature to it. But we can see that this will give us the best result in terms of sticking to the curve. And this again will work for a lot of magical type of effects. The problem with copy is that we can't layer microsolvers on top. So if I go to the shape tab over here and turn on turbulence, Even if I use a pretty high value, so if I use a value of 1, what's going to happen is that we are going to apply this turbulence only on one frame, but on the next frame is going to be overridden by the values from our velocity field. And we can see that for the most part, we have pretty much the same result. I will have to go pretty high to demonstrate this. So if I set this to 10, now we are starting to see a little bit of turbulence, but again, on the next frame, it gets completely overridden. So we have to rely on our velocity field. If you want to use copy, you probably need to increase the resolution of your velocity field. So if I set this to a lower size, let's use 0.2, let's reset, let's press play. Now, technically, we would have more detail in our swirls. We can go to our volume trails and maybe we can increase, in this case, for copy, the amplitude of our noise and play around with the settings more. But this can offer us pretty good results as well. So there is a case for copy, but again, typically we would like to use spool. Maybe I want to increase the acceleration strength here to 20. And now we can layer turbulence on top. So if I leave this with a setting of 1, which is a pretty high turbulence value, we can see we introduce a lot of noise. And probably this smoke is moving a little bit too fast. This is why it's not going to stick properly to our curve. Again, it requires finessing, but we can see that with pull, we still get the benefits of the microsolvers. Now, these kind of magical effects are typically done with particles that are later rendered as smoke because it's a lot easier to control points rather than volumes. So with points, you have a lot more shaping options. But still, this is to illustrate again that we don't have to rely on piling on microsolvers to force the motion that we want. So for example, inside our pyrosolver, I could add a, let's see, gas curve force. So this is a microsolver that's designed to do this effect that we want, meaning our smoke sticking to a curve. But I found that this is really a lot harder to control the smoke in this way, and it's just more straightforward with the velocity field approach. So now that we are more familiar with the operations here, let's start to explore more of the target fields that are available for us in a pyro simulation. So these ones over here. Let's go ahead and get rid of our velocity source for now, and we'll also disconnect our sourcing over here, and I'll just drag these over to the side. I'll get rid of this merge. So we just have our density source. Let's also go in the shape tab and let's disable turbulence so we don't have any microsolvers affecting our sim. Back to our sourcing. Let's go ahead and work on our temperature sourcing for now. So we can base this on the same source as our density. So in fact, I'm gonna go ahead, drag this over to the side, and while holding Alt, I'll duplicate this setup and I'll rename this null here. Let's type temperature source. For our VDB from polygons, let's also set this name here to temperature, and we'll also have to update our noise fog over here to look for this temperature volume. So let's type here temperature as well. And inside this volume noise fog, I will also want to change the offset so we get a different noise pattern from our density. And let's check, we have a temperature volume now, and this is a simple float field, so this will be a scalar field. Let's go ahead and merge this back with our density. And now in our pyrosolver, I can add a new source. This will be source name temperature, and target field will be the same, which is temperature. Again, this target field where it says temperature here, this has to be named temperature. For our source volume, for example, we could source in our density as our temperature, but since we made a separate field for this, let's just point this to our temperature from over here. So this is a scalar field, and let's leave the operation to add for now. And if we press play, we can see that nothing happens. So smoke rises when there's heat, and this is what the temperature will do for us. But in order for this to work, we need buoyancy turned on in the shape tab. So over here, we'll turn buoyancy on, and this is turned on by default when you drop a pyrosolver node in your network. And now if I press play, we can see our smoke rises. And because we have noise in our sources, we have nice swirly motions, even though we don't have any turbulence microsolvers affecting this. So if I were to turn off both of these noises for our source, and if I reset the simulation, we can see that our smoke simply rises straight up with not a lot of details and interesting features forming. Alright, so this is why it's important to always have noise on your sources. And again, we have two separate fields for this as our source for the density and temperature, but if I were to go to the temperature source volume here and point this to our density and just disconnect the temperature source, this will still work as we base our temperature field on the density source. And we have a rather similar result to what we had earlier. It's just that where our densities will have high values, this will also mean those are the areas that will rise faster than other areas as well. So this is why it's important to have a different noise pattern in the sources, because we want different areas of the smoke to rise faster, not necessarily the ones that have higher density. And we'll get back to this sourcing business in a bit. Let's go ahead and plug the temperature back and set this source here back to temperature. All right, so this overall just gives us a more random result. Now let's take a look at our buoyancy settings here. If we expand this window, we see we have quite a few settings here. Scale will be like an overall multiplier. So if I set this to a lower value, so 0.1, press play, our smoke will rise slower. We can also affect, let's set this back to 1. We can also affect the scale if we go in the sourcing and I set the source scale here to 0.1. This will give us kind of the same result, or rather the exact same result. And we can also affect the overall scale. I'll set this back to 1. If we go to our source volume in the volume noise fog here, we can go to value correction and we can just scale the overall value. So if I set this one to 0.1, we can affect how much temperature we are sourcing in, and this will have the same result. So sometimes you might want to change the scale directly in your source or in the sourcing tab here, or through some of the microsolvers like buoyancy in this case. Ambient temperature and reference temperature, for the most part, I like to leave untouched. This will also control how much the smoke rises, but I found that they're a little less intuitive. You might only need to fiddle with these settings if you want to get super correct, physically accurate results, but that's usually not the case. You might have a physically accurate simulation, but the creative director will come and say that he needs the smoke behaving in a different way, regardless if it's accurate or not. So honestly, for now at least, I wouldn't worry too much about these settings. More importantly, we can affect our gravity, acceleration, and direction. So first of all, we can see that the direction is set to -1, which usually means our simulations are going to point downwards. But in the case for smoke, it actually has the reverse effect where our smoke is rising up. But if we want to reverse the direction, we can just set this gravity direction to 0, 1, and 0. And if we press play, now our smoke is falling down. And the gravity acceleration will determine how fast it rises or falls. So if I lower this, we can see now that it kind of has the same result as our buoyancy scale. So for the most part, I like to leave the gravity acceleration to the default 9.8 value. And let's set the direction here back to -1. There's also some new settings here which have been added more recently. This density influences gravity option over here. So we can turn this on, and if we expand this window, we can map the gravity force based on how much density we have. And we can get really specific with these settings, and this is also sometimes useful, but I think we're stepping a little too much into the advanced territory here. For the most part, in this whole buoyancy tab thing, you will probably just need to adjust the overall scale and maybe the gravity direction. So if you want to make the smoke rise or fall down. And also we can control this temperature by going to the sourcing, and again we can play around with the operations. So typically with temperature we don't really want to add this and accumulate the values. You will often find operations being used here either maximum or pool. So if we set this to maximum, we will no longer accumulate our smoke, so it will have a more consistent rising speed. So now it doesn't have this kind of accelerating nature to it as it had with the add method. And with pool as well, we can also blend our temperature source values over time, and this is also capped. So I'll set the acceleration here to 10, leave the deceleration strength to 1, and if we press play, now it will rise a little bit more slowly and then settle for a consistent speed. So right away, just with buoyancy and with some noise on our sources, we can get a pretty interesting look. Let's maybe go to the Fields tab and I'll increase the dissipation back to 0.1 so our smoke is disappearing faster. And we can just step over to the Shape, or rather the Look tab real quick, and we can make this, let's shade this like fire, and I can turn off the smoke for now. And for our fire, this is currently looking at our flame field if we go into binding, so we don't have the flame field for now. Let's map this to our temperature for both intensity and color. And now we can see we have this simple fire simulation, and we can play around with the intensity in our look. So this can be something like a campfire or a candle flame. We can also maybe change the color here. So if I change the hue, we can make this blue or green, and we can very easily create some magical effects like so. Let's maybe just reset this color ramp and let's go back to our smoke shading. And we might as well just increase the density scale honestly here a little bit so we make our smoke appear thicker, and our shadow density as well. Temperature also have a few settings similar to density in our Fields tab over here. We have some temperature settings here. The cooling rate is sort of like the dissipation. The higher the cooling rate is, the faster our temperature will decay. So if I set this to a very high value, let's resimulate and let's press play. We can see that the smoke rises and then fairly quickly it loses temperature. So when it gets to maybe around this place, it no longer receives such a high temperature values. What this cooling rate means is that the temperature doesn't get carried further out as the simulation progresses as much. So we can see that our temperature starts to slow down our smoke at around this place. And if I were to have this a really low value, then our temperature will keep advecting our density at the same speed throughout this whole simulation. So now we can see that our smoke reaches further heights in the overall simulation. So this is the cooling rate. Let's reset this to the default, with which is 0.5. The diffusion, if we increase this, let's maybe set this to 0.5, this will blur our temperature field over time. It's pretty hard to tell, but we can kind of see that we lose a little bit of the finer details in our simulation. And a better way to illustrate what this is doing, if we go to the Shape tab, let's close this buoyancy tab, we have this viscosity option. So this is a blurring factor on our density field. And I'll set this to maybe a 0.2 value. These are rather sensitive values in both the viscosity tab here and also in the temperature diffusion rate. So let's go back to our Shape tab and let's reset our simulation. And now over time, our smoke simulation will blur out the fields, and we see that we lose a lot of those really sharp features. And this viscosity and also the temperature diffusion is very helpful when you're trying to make more stylistic kinds of simulations. But also we can see now that this resembles more like a candle flame. So there's definitely a place for viscosity and temperature diffusion. And like I said, this is a very sensitive value. So if I set this to a value of 1, this accumulates over time, kind of like what happens with the add operation in our sourcing. So we can see with a high value, we kind of lose the details that we get almost instantly. All right, so make sure that you don't use really high values here. Back in our Fields tab, there's also an option here in the temperature which says emit from flame, and we'll get more into this when we talk about the flame field. But for now, this is how the temperature field works. So let's maybe just reset the settings here. I'll set this to 0 and turn off viscosity. Let's take a look now at the next field, which will be Divergence. And for Divergence, we'll do the same thing that we did with our temperature. We're just going to go ahead and grab all of these nodes and duplicate these over. Let's rename this to divergence source, and for our volume in the VDB from polygons, we'll use name divergence, and we'll also use the same name here for our volume noise fog. So I'm going to paste this here. And also for our volume noise fog, let's again offset our noise pattern so it's different from the other ones. And we can now simply merge this in our chain. Let's go to our Pyro solver. We'll just keep buoyancy on for our shape tab, and in sourcing, let's add a new source, and we want to source in the divergence volume source into the target field divergence. So if we press play, not much changes, but if we increase the source scale here, we can use a value of 10 and play this now, we can see this expansion in our smoke. And typically for explosions especially, we'll use rather high values, so we can set this to 100, and now we can really see a big expansion, and this actually resembles more of a explosion kind of effect. Now again, we are continuously pumping in divergence, so we have this continuous expansion. If we wanted to have an explosion, we would fade out the sources over maybe the first 10 frames. So we'll see how this works a bit later, but this is what divergence will do for us. It will expand the smoke. And we can play around with the operations here and use maximum pull or any of the other ones, but typically for divergence we want to add this in. Now you might notice that the smoke doesn't continuously expand. We have our initial expansion and then it settles at around this scale. So unlike the temperature and density field, the divergence doesn't get carried over throughout the simulation. And this is also why we need such high values in our source scale. If we look at our divergence volume source, when the density gets pushed out and away from this area, it will no longer expand. So we really have this tiny area over here where we are pushing in our divergence values. This is why we need a high value in our divergence source scale to give our smoke an initial burst, and then it simply will get further advected by our temperature, microsolvers, and other fields. And we can simply increase our divergence source. So if I go to the sphere, we can just increase the uniform scale. So we can increase this entire volume for divergence. And if we go back now, we'll have a much bigger expansion. And in fact, let's maybe just decrease the source scale. Let's use a value of 10. So we have a bigger expansion now, but we can see that this is kind of feeling a little bit unnatural, and it no longer feels like an explosion. It no longer retains that burst type of motion, and that's generally what we want for explosion and most types of simulation. This slow expansion over time again falls more into the magical effects kind of category. So sometimes you might need to do this, but not that often. Typically you want short burst with very high divergence. So I'll go ahead and let's set this uniform scale back to 3, and let's set the source scale back to 100. So we want something that feels a little bit more like this. Of course, we are lacking a lot of details and we need to add noises, but as far as the burst is concerned, this feels a lot more like an explosion. Now, divergence can make the smoke expand, but it can also make it contract. So to illustrate this, let's just move our volume up. So over here in our divergence source, after the volume noise fog, we will append a transform, and we can just move this slightly up. Let's maybe move this around 3 units, maybe let's do 4. Let's go back to our Pyro solver, and in our source scale now, let's set this to negative value. So let's maybe use negative 50. Now as our smoke will rise from our temperature, let's press play. When it reaches our divergence field, maybe I can template, I'll just template the geometry for now, or actually maybe we can template this here, our volume. So this is where our divergence volume currently is. So when our smoke will enter the divergence field, it will start to contract and shrink. I'll maybe get rid of the template display, but hopefully we get the idea. We can see that we have this suction effect going on over here. So it's simply going to pick up the values from our divergence volume and it's going to multiply them with a negative value, and this is how we get this contraction. And we can play around with the source scale probably. Let's decrease this a little bit and let's see if this gives us a smoother result. So it's kind of working, but a better way to do this kind of suction effect is by using an SDF volume. So if we remember from the Intro to Volume course, SDF is a special kind of volume that stores the distance to the surface of an object, but it's still a volume, so we can also source it in our Pyro solver. So after we have our sphere over here, where we turn this into a fog volume, let's turn on the distance VDB. So this is the SDF. Let's use this option instead and turn off the fog VDB. And let's use the same name here. Let's type here Divergence, and we also want to fill interior because we will need to store the distance value inside this entire volume. So the distance VDB will store values that are positive on the outside and negative on the inside. So our divergence values will be 0 when it's right at the surface, and as we get further inside our sphere, we will have -1, then -2, and further into this negative range as we move closer to the center. So we'll have this natural gradient that increases towards the center here. And because we are working with negative values in our Pyro solver, we no longer need to set the source scale to a negative value because it is already negative from our SDF. So let's just set the source scale here to a value of 2. And I will also disable the volume noise fog, and let's make sure, let's go to our transform here and let's keep this where it is. Let's reset and let's press play and let's see if this works. So we kind of see something happening, but not so much. Let's, instead of increasing the source scale, we can go to our transform here. I'll press E to template this and I'll just increase the uniform scale. So we cover a larger area over here, and I might want to move this further up. All right, so let's maybe also increase the source scale. So the strength, let's maybe use a value of 3. And if I press play, let's remove the template display. Now we sort of start to see our smoke gradually contracting as it reaches the center of our sphere. Let's maybe increase this even further. A value of 5 should be fine. So let's press play. And now we get a really nice smooth. We can see that as our simulation enters this field, it's picking up the divergence values and it's contracting right towards the center of our sphere. So in fact, if I grab this transform and I move this over, let's maybe move this over to the side, and we should start to see this effect a little bit better. And the more I increase this scale here, the better chance I will give our divergence field to act on our smoke. So let's reset the simulation now. Okay, so now we can see it clearly as it travels from straight up. It will try to find the center of our sphere. In fact, if I remove the temperature and let's reset, let's go to our transform and press enter. I'll just move this over to the side. Let's just move this over completely to the side like so. And let's try if this works. And we can see that this works. Probably now the divergence values are too high. So let's maybe use a value of 2. Now we can see very clearly that it slowly starts to pull, and when it reaches further inside our volume, we get stronger contractions happening. So if we have to do a suction kind of effect like this, I would much rather use an SDF instead of the regular fog VDB. We could still use a volume VOP to turn our fog VDB to look inside and create this ramp ourselves, but the SDF gives us the values for free in a sense. So this is divergence, and this can make our smoke expand and contract. And the final field that I want to look into will be the flame field. Now, there are a couple more fields like alpha and CD, and usually we deal with those when we need to advect color information from a volume source, but honestly, that doesn't come up that often. We usually control the color through the shading tab. So if I go over here and I go to the look tab, like what we showed earlier, I can just change the smoke color from over here. So I can make this green or whatever. So we usually control the color after whether we simulate through the shading, but in very specific cases we might need to add vect color, so this is where these fields are necessary. And this also goes a little bit beyond the scope of this course, so for now I just want you to know that these fields exist, and maybe in a more advanced Pyro course we can focus on these. Anyway, back to flame. The reason that I saved this for last is because in order to explain what the flame field does, we need to know what temperature and divergence does. So now that we understand these two, we can talk about flame. So let's go back to Houdini and we'll just replicate the setup that we had so far. I'll just hold down Shift and drag this whole chain to the side. I'll go ahead and let's just copy all of these nodes, or maybe we can copy the temperature source rather. Let's go ahead and hold down Alt. I'll rename this here to, so typically we can see over here as well that I'm using burn as the name of our source volume. And this is what you will find in a lot of the pre-made Pyro setups from Houdini. And this is more of a legacy thing, so don't really worry about it. You can use whatever name you want, but we might as well just use this burn name. So this will be our burn source. Let's set the volume name here to burn. And in volume noise fog, we will also point this to our burn. And let's again just change the offset so we have a different noise, and we can now merge this with all of our sources. So let's plug this here. Let's go to our Pyro solver. In our sourcing tab, let's turn back on temperature and let's see actually what we have so far. So this is the simulation. Maybe we can increase the divergence a bit so it's pushing out slightly. Let's make sure that our divergence, let's set this back to a fog VDB. So I will turn this off. I will remove the transform, turn back on the noise. And in our VDB from polygons, let's turn off fill interior. So we might as well just introduce a little bit of divergence. And I'll just leave this at a scale of 5. We are just going to expand the smoke a little bit right at the sourcing over here. So let's add a new source and let's grab our burn volume, and the target field will be flame. And if we play our simulation, we can see that this doesn't do anything for us. For now, this flame field is just a simple field that gets advected, sort of like our density. In fact, if we go to our look tab, we can turn back on the fire here, and let's map the intensity and color to our flame field. So we can preview this. So I'll set this to flame and this one as well. So as it is right now, we are simply sourcing it in and advecting it, and it's not changing the behavior of our simulation. We can go to the fields tab over here, and inside the flame we can see that this by default is turned on, but it's going to need the burn volume source for this to work. We have the flame lifespan, which controls how much the flame lasts, so this is kind of like the dissipation for density. If I decrease this to a low value, so let's maybe use 0.2, we will see our flames starts to die out a lot quicker. All right, so we end up with something like this. And if we need a flame to last longer, we can just increase the lifespan. So this is in seconds, I believe. So right now it's going to last for roughly 8 seconds, which is almost the entire duration of our timeline. And the default value for the lifespan here will be 2, which is fine, which means that it will start to decrease at around frame 48. Now actually this value is not really in seconds, because if it were by frame 48 we should start to already have our flame dissipated. If we hover over the information, it says that it's the number of seconds it takes to use up a value of 1 in the flame field. And because in our sourcing we are adding, so we are accumulating the flames, we have really high flame values. So usually the operation for flame here will be maximum. We want to cap this at a source scale of 1, and this will now give us more consistent flame values. So we can see that by frame 48, because we are working with a source scale of 1, we actually start to see the flame dissipating at frame 48, which is roughly 2 seconds. So it's going to match this value that we are setting over here. Now don't worry too much about this. Just remember that the flame lifespan is like the dissipation. It's going to make the flame last longer or shorter, and usually in sourcing we want to use maximum as the operation. Now, this is the flame lifespan, so we are still currently not changing the behavior of the simulation. So remember what I said with divergence, that it's not continuously carried throughout the simulation, it settles at a given size. Well, if we want to keep expanding based on where our smoke is, we can use the flame field for that. So in our shape tab, if we go over here, we can turn on flame expansion, and let's expand this window. This expansion rate will determine how much divergence we are adding into the simulation based on where our flame is. And this flame range means that where we have flame values that are 0, our expansion rate will be 0, and where we have flame ranges of 1, our expansion rate will receive the full value of 0.7. Let's reset our simulation, and we can maybe kind of see a little bit of extra divergence where we have strong flame values. Maybe we can increase the expansion rate, and in fact, let's maybe just do a duplicate of our pyro solver, and on this copy I will turn off the flame expansion, and let's just move this over and merge this so we can compare with and without flame expansion. I'll drop down a merge, and let's maybe move this even more to the side, like so. All right, so our first copy, this one in the center, will have the flame expansion, and this one will not have. So let's press play and simulate. We can see that for the most part, we have the same result. We might have a little bit more expansion over here, especially where we can see with our shading on the values of our flame that these parts here that are brighter will receive a higher divergence rate. So we can compare this part with this part, and we can see that this is slightly bigger. Now we can increase the expansion rate here to amplify this behavior, or we can make it easier for our divergence to find the flame range. So if we compute range, we can see that currently in our simulation, our highest flame value is this 0.6 value. So this means that only the highest flame values will get the full expansion rate. And again, to make it easier for our expansion to take place, we can lower this threshold here. So let's set this to 0.2. So now if we resimulate, we can see a much bigger expansion. So maybe now we can dial the expansion rate back to 1. So let's press play. And now we can see we have a lot more divergence based on our flame field. So even after we escape our initial divergence volume source over here, we'll still expand our smoke again based on this flame field. So this is why the flame field is important, and this is also how a lot of explosions work. We need this continuous expansion throughout the simulation. And for a lot of microsolvers, we can map the behavior based on different fields, and we'll take a look at this in a second. But for example, we can also remap the flame range. So this is now currently going from 0 to a value of 0.2. But let's say that I want to have the most expansion rate right in the middle at 0.1. I could just modify this ramp here to receive the full value in the middle and not receive any value at all. So now a flame value of 0.1 will receive the full expansion rate, and the highest flame values of 0.2 will not receive any expansion. So we have kind of this smooth progression for our expansion rate, and we can kind of see this happening here a little bit. This kind of ramp will provide pretty smooth results. Maybe I can increase the overall expansion rate here to see this better, and we can kind of see a difference here. But for most cases, you can use just the default ramp. In fact, you can turn this off, and this will be just fine. So flame can help us with the divergence, but it can also add in more density throughout the simulation. So if you go to the Fields tab, in the Density tab over here, let's maybe collapse these for now. If we look at our Density tab, we have this option Emit from Flame. So if I turn this on, now we are going to continuously pump density as well where the flame values are. So again, we see that we are using this flame range from 0.2 to 0.5, and I believe this should be fine. We can also set the operation to maximum or add. So if I reset the simulation, hopefully we should see a little bit more density, and we do. But for example, if I go to the sourcing tab, I can turn off the density, so we actually don't really need to source any density at all, because our flame will create density now. So if I reset the simulation, we start without any density as our original example, and as we progress further, we can see that we add density where the flame values are high. Okay, so this is also something that happens in smoke simulations. And we can go to the fields tab here, and if we really want to add a lot of density, we could set the operation here to add instead. So now this will thicken our smoke a lot more, because again, the add operation will make us accumulate density. So we can see that it's really a lot thicker. But the operation by default is maximum, which will be okay in most cases. We can also again remap the flame range, and we can see now that Houdini gives us this kind of ramp that we created earlier. So this is the default Houdini suggests that we use, again, which will mean that we'll get higher density values in the middle of this range. So we also have control over this. All right, so from flame, we can add divergence, we can add more density, and we can also, if we go to temperature, we have the same option, emit from flame, and if we turn this on, we can keep adding temperature to our simulation, which will make our smoke rise even more based on our flame range. So now if I play, we might want to decrease the flame range again for our values to be easier to match, and we might also increase the strength here. We can see that the default operation is pull. We can also use add, but it's really not recommended with temperature. Let's leave this at pull, and let's take a look now, and we can now see that the smoke rises really fast. And again, this will also work if we didn't have any temperature to begin with. So if I turn off the temperature here in the sourcing, we will still get the rising behavior in our simulation because our flame field is continuously adding temperature. So hopefully this gives you an idea on how the flame field works. With flame, we can add more divergence, more temperature, and more density throughout the entire duration of the simulation. So not just in the beginning where we are sourcing our volumes. Now that we have a better idea on how the sourcing tab works, let's take a deeper look in our shape tab and explore some of these other microsolvers. Let's go ahead and just clean up the setup a little bit. I'll go ahead and remove our duplicate. Let's focus on our Pyro solver. Let's see what we have so far. So this is all right. I might want to go to buoyancy here. Let's maybe set this to a lower value. 0.1, and in the sourcing tab I'll turn back on density and also temperature. I'll keep these other settings as they are. Let's take a look. Alright, so we have just a slight expansion, kind of like a smoke bomb or something, and this will be fine just to demonstrate our other microsolvers. So in our shape tab, we have buoyancy, flame expansion that we know so far. Let's turn on wind and let's see what we get. So this is pretty straightforward. We are simply going to push the wind in a direction which is currently on the X. If I increase the speed, maybe we can see this better. All right, so again, very simple and straightforward. A very annoying gotcha with the wind is that if you have this wind option turned on and you want to later advect particles by this pyro simulation, you have to go in the output tab and turn on this add wind to velocity field option here. And I don't know why this isn't turned on by default. If you don't have this on, you will not be exporting the correct velocity information. And again, this is only relevant if you have this wind option here. Alright, so this is wind. Let's turn this off and let's turn on disturbance. By default, our disturbance value of 0.5 is rather low, so we can see that nothing changes. So I usually like to go rather high with this value, so let's use a value of 10 here instead. And now if I press play, we can see this disturbance is like a very high frequency noise that gives us a lot of breakup that later forms into more interesting features and shapes. So disturbance is really important in a lot of pyro sims. Let's take a look at some of the settings, and the default mode here will be block based. We also have continuous, but with continuous we can see that this works and it has some use cases, but we don't really have a lot of the settings that we have with block based. And in general, block based, I found that It produces more variations in the scale of the noise that is applied, so this is what I would recommend in most cases. So block size, roughness, pulse length, all of these settings we are pretty familiar with from other types of noises in Houdini, and feel free to experiment with these. So if you want more roughness, or if you want the noise to animate faster, you can change the pulse length, so you can decrease this here. But for the most part, I found that the default settings give pretty good results in most cases. Now, threshold field here is mapped to density, and this range should be fine in most cases. What this means is that where we have a density value of 0, we get the full effect of our disturbance, and where the density is higher than this 0.05, it will scale down to 0. This means that, for example, if I zoom in on here, where we don't have density, so right outside of our simulation, we apply the full force over here of our disturbance up until we pick up a little bit of density. So over here, maybe where the values increases to this 0.05, we no longer apply our disturbance. And this means really that it affects the density only on this tiny sliver at the exterior of our simulation, so sort of our silhouette, so to speak. If we were to apply this disturbance further inside, I could increase the threshold range here. Let's maybe try a value of 2. So now we would apply this noise all the way inside, maybe to around here, where we would start to have higher density values. So maybe we can actually compare. I will reset the simulation and duplicate this over. Let's set this threshold range value, our first one, to 0.05. Let's actually decrease this even more. So now only the very exterior of our simulation will be affected. And for our first one, we'll leave this at a value of 2. So let's go ahead and just add a transform, and I'll move this over like so, and just simply merge these two so we can compare. All right, and let's simulate and see what we get. Let's give this a few frames. All right, so hopefully this kind of look the same, to be honest. Let's maybe just increase the disturbance in both cases. So I'll use a value of 20 for both of these, and let's resimulate. But we can kind of tell already on our first version here, where our threshold is higher, our disturbance is allowed to go further inside. And on our second example, where we have this low value, we only get disturbance right on the edges. So if I simulate further, we can kind of see in the center of our simulation, we don't have as much disturbance as we have over here. So this is what the threshold range will do for us. So let's maybe disconnect this. Let's go back to our initial example. Generally, you don't really have to mess around with the settings here for the threshold field. These defaults will be fine in a lot of cases. Let's take a look at control field next. So let's turn this on. And we learned a little bit about this control field when we were talking about the flame. And it's also similar to the threshold range option here. And we can see that in the case for disturbance, Houdini by default maps this control field to a field called speed. And this speed field is simply a field that stores the length of the velocity vectors. So it simply says how fast we are going in any given voxel. Now we don't have this speed field by default. To create this field, we have to go to the Fields tab, and we have to turn on the speed option over here. So this will compute for us this speed field. Now, this isn't turned on by default because it slows down the simulation, but honestly, it's not gonna slow it down that much. So in a lot of cases, we do need to compute this speed field, but this is why it's not turned on by default. So after we turn this on, now in our Shape tab, we do have this speed field. And this range here will simply say that if we have a speed of 0, so we're not moving, scale this disturbance value to 0. And when we have a speed of 1 or greater, scale this all the way to 20. So values over 1 will still only receive the full value of 20. This won't keep increasing if we have speed values greater than 1. Now, this is great because the default behavior of the disturbance is to continuously break up our smoke over the entire duration. What we usually want is to break up our smoke initially as we start. So if I press play and we start, we have a lot of nice breakup. But after we break up our noise and we have those features forming, I don't want to keep breaking up the smoke. I just want to normally advect it to have a nice variation between large and small shapes. Now we don't really know what our top speed here is, so what I usually do is I just simulate a few frames of our simulation, and then if I click on this compute range, we see that our fastest moving voxel has the speed of 7.6, and if I go maybe in the beginning and I hit compute here, we see we have a value of 5.5. So this is our top speed. So let's make it easy for our disturbance and say, all right, if your speed is, let's say, maybe 2 or above, you'll get the full disturbance. And if your speed is lower than, let's say, maybe 0.5, so if you're moving really slow, like we showed after the simulation progression and it starts to slow down, let's no longer apply the disturbance. So values lower than this will not have this disturbance. It will scale this back to 0. So this simply means that when our smoke starts in the beginning and is moving fast, and after some time, as it slows down, we are no longer breaking it up. And let's maybe also make a comparison for this. I'll just delete this duplicate, and I'll make a new one. So let's connect this here, and I'll turn off the control field for this one, and let's merge this here, and this one has the control field, so our first one in the center here. So let's press play, and we can see right away in the beginning that because we haven't really picked up speed yet, this version over here doesn't really have a lot of breakup, so disturbance, and this one on the right, where we are not controlling it by the speed, will already start to break up. So if we simulate some further frames, we can start to see this one has a lot more breakup, and this one has some breakup, but we have more variation with larger shapes. So we only have breakup in certain places, and this again will give us a lot more variation, and it's going to look a lot more interesting. Now these still look rather similar, and with disturbance in general you need to use higher resolutions. So we'll talk about the setup in a second here, but let's just increase the resolution here. Let's set this to 0.05 on both of these versions, just to add more resolution, and I might want to just move this further out. All right, and if I press play now, obviously we're going to have a slower simulation, but we can start to see a lot more detail, and we can already see that this one has a lot more disturbance, which is something that you might want. But again, as the simulation progresses, we see that we end up with too much breakup on this version, and we only have again the breakup where our speed reaches certain values. So overall, it just introduces more variation. We can also control, let's go back to our shape tab. We have this option to remap our control field if we really want to get super specific, but honestly, this doesn't come up that often in the case for disturbance, so don't worry about this setting for now. Moving over to the next one, we have Turbulence. So we are already familiar with Turbulence. We have all of the settings that we are used to by now, and generally here I only like to play with this Turbulence and swirl size settings. So Turbulence is the strength, and swirl size will be how big our noise is. So generally, I don't really play around that much with roughness or pulse length. In fact, I can reset these values. If I want to add high frequency detail, I will just use the disturbance instead. So I generally use the turbulence to get our larger swirls and then leave it to disturbance for the high frequency, smaller noise. And we can also control this turbulence based on other fields. So in the control field here, we could say that we only want turbulence where we have high density values, or we can map this to our flame field or any other field. So hopefully by now you get a sense of how this stuff works. Shredding is also a type of noise, and this is based on the Disturbance microsolver. In fact, we can see that over here we have kind of the same settings that we have in our disturbance. The difference with shredding as opposed to the disturbance is that shredding will keep the speed consistent to what we already have, while disturbance is also changing the velocities a bit. So I'll set this here to a value of 10, and if we press play, this is currently mapped to our flame. So we don't currently have such high flame values. So let's go ahead and instead of 1 here, let's do 0.3. So now where we have flame, we are also going to break this up even more on top of our already existing disturbance. And think of this shredding like extra disturbance we can add while preserving the overall shape of our simulation. So sometimes I might use this, but a lot of the times I just like to use the regular disturbance. But this is what shredding will do for us. Finally, we have a flame expansion, which we already know, and viscosity will introduce a blurring factor to our simulation, and it will smooth out the features over time. So if we press play, we can see that very quickly we no longer retain a lot of the nice crisp features. So this is again a sensitive value. I would generally use very low values here. So let's maybe try a value of 0.1. So we have our features in the beginning, and as our simulation progresses, we are going to blur out and smooth out the simulation more and more. So we can see we can get some pretty good results with this as well. Maybe a low value here for viscosity will work pretty well in most cases. Now, on top of all of the microsolvers exposed for us here, we can step inside of the Pyrosolver and we have access to all of the microsolvers now. So this is the gas curve force that we talked about earlier. And really, if we hit tab again and if we type gas, we can see that we really have a lot of microsolvers that we can try. Now, you can achieve almost any look just by using these microsolvers here. But as you get more advanced and you want to get more specific, you might need to add some extra microsolvers on top. So one pretty common one will be gas vortex confinement. So if I drop this down, this is usually used to preserve the swirls in our simulation more. So generally, as the simulation progresses, our velocities slow down and we no longer add these swirls to the simulation. So this is used to accentuate those swirls and keep them on for a bit longer. So it is sometimes useful, but one microsolver that I commonly use is going to be the gas damp. So if I connect this here, this is like a drag force, and this is very useful when you want to achieve a slow motion kind of effect. So when you have a super fast motion that you want to slow down fast, you can use this microsolver. By nature, pyro simulations will slow down as we run out of temperature and density over time, but this will act like a global multiplier on our velocity field. So it forces the simulations to slow down sooner. So if we press play, we actually have to preview this at the top level. Let's maybe pin this viewport here and let's step back inside. All right, so if we press play now, we might not see this right away, but what this is doing is it is applying a factor of 0.1 on our velocity field until it reaches this target speed of 0.1. So if I were to increase this to 0.5, this would mean that we slow down faster over time, and if we set the target speed here to 0, we will freeze this entirely after a while. So if I press play now, we are simulating for a bit, and very quickly we should see that after a bit the smoke stops moving entirely. And we see that because we are affecting the velocity fields, we are losing almost all of our features as well. But again, this node is sometimes very helpful when you want to achieve more specific super fast to slow motion kind of effects. Or I also use this microsolver sometimes when I'm having a hard time controlling smoke that is moving super fast. So I might want it to start off pretty fast to get our features, but then I want to slow it down. So this is where gas damp comes in handy. Anyway, these are the microsolvers. So now that we have our sourcing and we have our microsolvers, so our shaping, we can talk about some of the other tabs inside the Pyrosolver. Let's now talk about the setup tab. So here we have the voxel size, and if we lower this value, we will increase the resolution. But this naturally will increase our simulation time, but you will get more resolution in the simulation. So the general workflow is that I usually set a higher voxel size when I'm doing tests, and while I'm adjusting the sourcing and microsolvers and all the other settings, I want the simulations to run as fast as possible. And then when I get roughly the look that I want, I start to decrease the voxel size to get higher resolutions. And then finally, I will settle for a final resolution on which I do the file cache. So I might set this to something really low, like 0.02 for the final resolution. And after this, I would do the file cache and save it to disk. We have an option here, velocity voxel scale, and this has been added more recently. So if we increase this scale here, it means that our velocity field will have a lower resolution. So this will in turn make our simulations go a little bit faster, but we might lose some of the detail. Now, in the case where we have this container type vectored field like we created over here, like this, we have the option to set the resolution of this velocity field directly from our VDB from polygons, or in this case from the VDB over here. We can set the size that we want, but in a lot of cases, and we'll see this in a bit, we don't actually have the velocity sourcing as a separate field that we can adjust. So this is where this option is useful. And like I mentioned earlier when we were talking about velocity fields, if we are in fact losing too much detail, we can add some of the detail back with Microsolvers. Timescale is pretty straightforward. It will increase the speed of our simulation overall. So this is also something you'll have to adjust usually. For fast moving smoke like flamethrower, this is worth increasing to maybe 1.5 or even 2, and if you have slow moving smoke like fog on the ground, you might have better results with a lower timescale. Generally, I wouldn't go with timescale values above 2 here, so if I really wanted faster moving smoke, I might go up to 1.5 or 2, but if you go much higher, you'll find that it's really hard to control the simulation. You'll start to get very erratic behavior, and a better idea is if you really want the smoke to be moving faster, but you still want to retain some of the control, the better workflow is to simulate this at a more normal timescale and then just do a retime after. So this is post simulation. So we'll talk more about the retime maybe in another course. It goes a little bit beyond the scope of this PyroSolver course. But you can in fact speed up the smoke or any simulation in general after you simulate it, so not during the simulation. Now back to our settings. Global substeps and minimum and maximum substeps are general simulation parameters you have on most solvers. By increasing the max substeps, you will get more accurate simulations. So generally with fast moving smoke, and especially if you increase the timescale as well, you will probably need to adjust the max substeps to maybe a value of 2 or even 3. And generally I wouldn't go higher than 3. In most cases 2 or 3 is more than enough. Global substeps is useful when you have fast moving sources outside of our PyroSolver. So these sources over here, if these any of these would be animated and moving very fast, then you will have to increase the global substeps to account for this change in the sourcing as well. However, usually we like to optimize our sources directly to account for fast moving motion, and we'll see this in action later. So I don't find myself often increasing the global substeps here. So for the most part, let's not worry about this too much. This advection reflection thing here is also useful when you have fast moving smoke, especially. By default, this is disabled, but we can do single project or double project. So either of these options are fine if we choose single project. The thing that happens usually with smoke simulation is when it is moving too fast, it tends to lose a lot of the velocity information due to pressure. So advection reflection attempts to counter this by bringing back some of that velocity. It's a pretty useful feature, but honestly, it makes the simulations pretty slow, so I don't find myself using it that often. If I'm losing velocities, usually I like to correct that with Microsolvers or other settings. Now, in the simulation type, we have by default sparse, which means that as the simulation progresses, we are only going to add voxels as needed in order to run the next frame of the simulation. And if I press W, we can kind of see this happening. We see that as I play the simulation, so as we progress further and further, we expand dynamically the bounds of our simulation. So this is why it's super fast in the beginning, and then it starts to slow down as we increase the domain, so we have more voxels to take into account, and the calculations overall will be slower. And we also have this minimal OpenCL option here, which will use the GPU to perform the calculations, but we are then tied to a specific bound. So if I press enter, we will be only able to simulate in this domain, and all of these voxels will be activated at the same time. but since this is running on the graphics card, this will be much faster. So if I press play, we can see that we almost have real time, and we can also see that when our smoke escapes this bounce, it will no longer get any density, so we are contained within this box over here. So naturally we can expand our bounds to get the benefit of the OpenCL, but as we increase the resolution, so if I set this to a lower size here, we see that we are already operating on around 400 million voxels, and this will be still pretty fast for the most part, as we can see. We can also see with OpenCL we can cache this in our timeline. We have to do a file cache in order to save this to disk, so we can then play it back. So this is also one of the drawbacks of using the minimal OpenCL. And we are also limited by our graphic card memory. So if we preview our simulation and also open the task manager on the GPU, and let's resimulate, and let's run this while we are looking at our GPU, we can see that right away I'm using around 40 gigs. So because I have 24 gigs, I might still be able to push this even further, so the resolution, or increase the bounds, but obviously this requires that you have a rather beefy video card, and this will be the limiting factor. While with sparse, we don't have to worry about this. We are storing it in our video RAM and then onto disk. So with sparse mode, we can push the resolution a lot more usually. But we can still use the minimal OpenCL to our advantage. We can simulate at very fast speeds at a lower resolution. So if I play this now, we see that we get super fast playback. So we can do tests and adjust our settings, and then when we get the simulation looking roughly how we want, we can set this to sparse and we can lower the voxel size, and then we can cache this out. So you can leverage this minimal OpenCL simulation type to your advantage. Another one of the drawbacks of using OpenCL in our setup simulation type is that some microsolvers might not work in OpenCL mode. So for example, if I step inside and I drop down a guess disturb node, we can go to the advanced tab, and if we want to use the OpenCL simulation type, we also have to check this option here on our microsolvers. So a lot of microsolvers don't have the OpenCL option, and again, this is one of the drawbacks, but usually if we go to our shade tab, all of our microsolvers here will work by default when you turn on OpenCL. On the bounds tab, we have the option to expand the domain when using minimal OpenCL, so I can increase the size here, or I can press enter in the viewport and adjust the handles to accommodate for a larger area. And if I go back in the setup and set this simulation type back to the regular sparse mode, in the bounds tab, this option now is disabled by default, so the smoke is allowed to expand infinitely. We can, however, still turn this on, and this is useful when you want to clip the smoke that's outside the camera. So if we had a camera, let's say that it's more up close, and if we press play and simulate, we can see that a lot of this smoke goes outside the camera, so up here at the top. So it would make sense to limit the bounce. So if I press enter, I could just decrease the upper limit of the smoke simulation, so we don't have to simulate any parts that we are not going to see either way. So let's maybe reset the size, or actually let's just turn this off. And in the resizing tab, we have some very useful options here. This padding determines how far the domain is allowed to expand to accommodate for the simulation. So for example, if I had very fast moving slow, let's go to the sources. And also in the sources, when we switch to OpenCL mode, we turn on this option here to limit source range. So now if I play the simulation, we will only source in our volumes for the first 12 frames, as it is set in this range here. So we can see that we are not continuously pumping smoke. And again, we are turning on this option by default when we are using OpenCL, but the regular behavior for the sparse mode is to have this off. So I will just turn this option off so we can have continuous emission, so we don't have to worry about our sources disappearing. Alright, so back in our source volumes, in our divergence, let's say that we have a huge size here, so let's set this source scale to 50. and make this a huge explosion. So if I press play, let's maybe make this even higher. So let's use 100. Okay, so now we are starting to see, especially in the beginning, we can see the smoke gets this kind of blocky look to it in our first frames, kind of like the smoke is trapped inside a cube. And this is where our padding option comes into play in the bounce tab. By increasing the padding value here, we give our smoke more room that it can fill up as it expands and moves. Now, increasing this value will slow down the simulation a bit, so make sure you just use the minimal amount necessary for your simulation. So if I press play now, we kind of still see a little bit of the blocky look, so maybe I can just increase the padding more. So now we can see in our first frame we retain this kind of nice sphere, whereas where we had a very small padding value. So if I press play now, we can now obviously see the bounds of the domain cutting off the smoke in this kind of like cube. So this is where you would have to increase the padding. Now this is also fixed usually if you increase the maximum substeps here. So if I increase this to a value of 2 and leave the padding at 0.3, now this value will sort of apply in between the simulation frames. So if I go forward a few frames, we can kind of see the padding a little bit, but it's not as bad. And the more I would increase the simulation substeps, I would get rid of this blocky look, but sometimes when you have really fast moving smoke, you would still have to increase the padding. The reference field tells the simulation which fields we should look at to base our padding on, and generally density and flame is fine for this, but obviously if you only have temperature or something, you would have to specify this here. And then we have a few more options and some that concern looking at the velocity to expand the padding, but for the most part I don't really mess around with these. The most important thing here is going to be the padding value. Let's look into collisions next, and for this I'll first go to the sources here and I'll just get rid of divergence and flame. And also let's go to the shape tab and increase the buoyancy here to maybe 0.5. So let's see what we get. We just have this simple smoke rising simulation now, which will be fine. So let's go ahead and drop down a box. I'll place this over here and I'll press enter. I'll grab the handles, hold down shift, and I'll just scale this on the X and Y and the Z direction, so we just make it a little bit more stretched. Let's go ahead and after this I'll drop down a transform and I'll press enter and I'll just move this over and maybe also move this on the side. Alright, so let's turn this into a collision. And I'll also place down a null here just to keep things organized, and let's rename this to collision. So I can plug this directly inside the second input of the Pyro solver, and now inside the collision tab this is by default set to collision geometry. So if I reset the simulation and press play, we should see our collision with the box, and we do, so everything works. And this use deforming geometry is turned on, so in case we had some animation on our geometry, it would pick that up as well. Now we have a few options here, but really what's happening under the hood is that we are turning this geometry into a volume and calculating the collisions at the volume level. So even though in our Pyro solver it says here collision type geometry, we are still just doing volume collisions. So instead of this type, this collision geometry type, I will highly recommend that you use SDF plus volume velocity instead. So this is now looking for an SDF volume named collision. So let's go ahead and after our transform, I will do a VDB from polygons. Alright, and let's preview this. So this creates an SDF for us based on the geometry, and we have to set the name here from surface. Let's rename this to collision, so it has to match the name that we set up in the Pyro solver as well. So it has to match this name we set here in the Pyro solver. And now we have complete control over our volume collision. So for example, we could increase the voxel size here, so we could reduce the simulation. So if I set this to a value of 0.2, we are still going to get collisions here, and this will make our simulation a little bit faster. Now, the collisions, no matter what, will still happen at the voxel size we specify in the Pyro. So in our setup, the collisions will happen at this resolution regardless. But setting the collision volume to a lower resolution will mean it's faster to read in, and it can help make the simulations a little bit faster. The problem is that you might lose some accuracy, so it's up to you to find the right balance depending on the shot you're working on. But a general rule of thumb is that you should have at least the same size as you are using in your Pyro solver, so I'll just set this back to 0.1. Now, our Pyro is looking at this SDF to create the collisions, and it's very important that we store enough information around the geometry. Otherwise, the smoke might not pick up this SDF field. So if I had really low exterior and interior band voxels, if I set this to 1 and 1, so we just have a row of voxels with information around our geometry, so to speak. If I reset the simulation and I check the result now, we can see that it still kind of picks up the collision, but some of the smoke, especially the smoke that is moving really fast, is actually going inside our collision volume. So this is why we have to make sure that our band voxels are high enough, and in fact, we should just simply fill the interior, and we can see that already we now got rid of all of this smoke. So by filling the interior of our SDF collision volume, we ensure that the smoke is never allowed to step inside our collision. So now if I reset the simulation, we see that we have the proper collision, so no smoke is going inside where we don't want it. Now, we also have this velocity volume option here for our collision, which is looking for a volume called V. So if we had moving geometry, we can transfer some of that velocity to our simulation. And let's go ahead and go to our transform, and maybe at around frame 35 to give our smoke enough room to advect first. I'll move to frame 35, I'll press enter, and I'll just drag this over, and with Alt and left click, I will add a keyframe on this value here for the Z component, and maybe just go forward a few frames and just drag this over, and this will add another keyframe for us. So we have this animation here, and I want this to be rather fast in order to illustrate the point more clearly. So maybe I can scale this animation, but something like this is fine. So let's say that we have animated collision. Let's do a trail stop after our transform, and we want to compute velocity over here. So now our points, if we turn on point trails, we can see if we move inside this animated frame here that our points have this velocity value attached to them. And now we can transfer this point data into our volumes. So in our VDB from polygons, let's go ahead and click add one surface attribute. So let's hit plus over here. The attribute name will be this point V. So this will be our velocity data. And the VDB name will have to match this volume name here in our Pyro. So I will name this VDB name. I'll set this to V. And the vector type that we want here is going to be displacement, velocity, acceleration. So this again goes back to the intro to volumes course. And this is typically what we want for velocity volumes. Now this should work for the most part, but just to be safe, let's cover a bigger area of our box geometry with this velocity information. So in our box, I will just increase the axis divisions. If I press Shift W, we can just increase the resolution. And now if I go to the trails, we can see we have a lot more points containing this velocity information, so it will be easier for our volumes to pick up the correct values. And now if we reset the timeline and I play the simulation, let's see what we get. Alright, so as our box starts to slice up our smoke simulation, we have the collisions happening, and as the box passes through the simulation, we can see that some of the velocity from our box gets transferred over to our simulation. So we have this nice natural movement. And this is what would happen in real life if we had this kind of animation. So we have these nice swirls as the box passes through, and this is super helpful because a lot of Pyro simulations have collisions elements. So if you think of a building destruction or really any kind of destructions where we have chunks and debris falling everywhere, we want to transfer those velocities to our pyro, and it will instantly give us a lot more details and features. So if I do an example here, I'll reset the simulation, and let's just do an example where we don't have the velocity transfer. So I'll just move this over to the side. Let's merge this over, and I'll do a separate collision for the second one with a separate VDB from polygons. And here I will just turn off, I will set clear, so we don't have a velocity volume, so we just have the collision. And on this one, we also have this V volume. All right, so now if we check the different results, we can clearly see the difference now. Where we have our velocity volumes, we pick up the velocities from the collision geometry, and we have a lot more swirls and details, and just in general a more natural movement of our smoke. Whereas here we still have the collision, so we can see that the simulation still gets sliced when our box passes through, but that's the only thing that we are doing. We are not really affecting the velocity in any way. So usually, especially if you have moving geometry, you want to leverage the velocity volumes here. Now we have to be careful with the naming here, because we can see that this is named V, and if we go to our velocity field that we created earlier, we also set the name here to V as well. So if we had an additional source inside our Pyro solver over in our sourcing tab, if we are also sourcing a volume, a velocity volume, we have to make sure that it's not named V if we also have volume collisions that are named V. So in this case, if I had an additional velocity volume as a source, I would just probably set the name here to vel or just something else. So we just have to make sure that this doesn't have the same name as our collision velocity volume. All right, so let's get rid of this duplicate. In the ground plates tab, we have the option to collide with a sort of like an invisible surface. So if I were to turn on the Y ground plate, we can say, let's do close the below, and we can see that automatically we slice our volume in half, because this is right on the center of our scene, so it has a height value of 0. But if I were to decrease this a little bit, we can offset where this invisible plane is. Let's maybe do -1, and if we press play, it will now collide with this ground. Now it's going upward, so there's no collision. Let's maybe just say closed above, and let's increase this to maybe a value of 1. So now we should have collision at the top, and if we press play, we can see we have this collision with this sort of invisible plane, and our smoke has this nice spreading effect. So this is a really quick way to do shock waves, for example. If we want to do a shock wave, we will always need to rely on this collision for this spreading effect to occur. So this is very useful a lot of the times, and we can close the boundaries on the X or the Z plane, so it's a very useful feature. I'll set this back to open, and we can also collide with a height field. So if I were to have a height field in our scene, let's maybe just make this a lot smaller, and I'll increase or rather decrease the grid spacing, so we increase the resolution. And let's also maybe just add some noise, so HF noise, and I'll decrease the amplitude and element size quite a bit over here. Let's maybe use a lower element size and also amplitude. So we just want to introduce a little bit of noise, right? And let's take a look at our simulation. Let's just move all of our sources up a little bit. I'll do a transform, and I'll just grab this and move this up. And in the buoyancy tab here, let's set this to a negative value, so our smoke falls down. And let's say that we want to collide with this height field. I'll just drop down a null here just to keep things organized, and this will be our height field collision. I will Control C, grab this null, and let's paste this in our Pyrosolver collision tab. I can turn this on, and I can just paste the path to our null over here. And now if I press play, when our smoke falls down, it will collide with our height field. So this is also, we can also see we have this collision with our box as well. This is why we drag this smoke along, but we can see that our height field collision is working. So height fields by nature are volumes, and this height field collision is really fast to calculate, so it's really powerful. And we can also turn on use deforming geometries. So if our height field was animated, for example, if I were to animate the noise, we would be able to transfer that over if we turn on use deforming geometry. Of course, this will slow down the simulations a bit. But this is pretty much it for the collision, and really the only tabs that we have left here is the look tab, which we touched on briefly. Now, we are not super interested in this look tab that much because a better way to shade the fire will be by using a pyro bake volume, and we'll take a look at that in a second. And the only other tabs we have left is going to be the Advanced tab, which has a lot of options that we really shouldn't mess around with for the most part. I rarely have to step inside any of these settings, and really these settings are more for very specific use cases, so you don't have to worry about these. And then we have the Output tab, where we can choose which fields to export. By default, we have a lot of fields, as we can see. Now, generally, we need to export density, temperature, and flame for the shading. And we also need to export our velocity field if we want to later do motion blur or, more commonly, advect particles by the smoke simulation. And then CD if we are advecting color. So we can choose which fields to export here. If I just want the density, I can turn all of these other ones off. So I'm only concerned with density. And then we also have the option to convert this to VDB. So by default, we are exporting this as standard Houdini volumes, which, as we talked about in the Intro to Volumes course, are more inefficient than VDBs, so I will recommend that you use this convert VDB, especially since if you want to render the volumes in Solaris later, it will require the volumes to be VDBs. And then if we use 16-bit float, this will optimize the volumes a little bit, so they don't store as much space on your hard disk and they're faster to read. So this is also a very useful feature. And all of these other settings as well have to do a little bit with optimizing the volumes, so they read back a little bit faster. So for example, we can resample the velocity field to be half the resolution. So if we increase this voxel size to a value of 2, we essentially lower the resolution in half. So usually for motion blur, you don't really need to carry a lot of the details from the velocity field. But if we want to advect particles, we might need the full resolution of the velocity field to have all of the nice swirls and details carry over in our particle simulation. So you should use these options on a per case basis. But VDB and 16 float are pretty useful usually, so you can use these in most cases. So now that we are familiar with all of the tabs, we can talk a little bit more about stuff that happens outside of our Microsolvers, so mostly with our sources. Now, this setup here that we kept using, we have each source as its own separate thing. This setup is not really what you will often see. I only set it up this way to illustrate what the different volumes do. Usually you will base all of the volumes on the same geometry. So maybe I can just go ahead and I'll just grab one of these spheres and I'll just drag this over. And we can start fresh in a new chain. So the more efficient setup is to create point attributes on the surface of the sphere and create different attributes for the different volumes. So we have a density attribute, a temperature attribute, and so on. And then we can turn all of these attributes into volumes at the same time with a volume rasterized attributes. So from our sphere, we can do a scatter and we can just increase the total count here until we fill up the surface. And then inside an attribute VOP, let's drop down an attribute VOP, we can go inside and we can start creating the attributes that we need. So we know that in our sources, we usually want to have noise and breakup, so we can base our attributes on a noise. From our position, I'll just drop down a turbulent noise. And I know by default, the turbulent noise outputs values between -0.5 and positive 0.5. So let's do a fit range. And we want to remap these values. So again, source min -0.5, source max 0.5. We want to remap these values to 0 and 1. And generally, you don't want to be using negative values with a lot of the volume sources. We might want to use it for divergence, for the suction effect, but we shouldn't have it on the other fields like density, temperature, and flame. So from here, all we have to do is do a bind export. We can also preview our noise pattern if I plug this inside the CD, so we can kind of see this here. Maybe I can play around with the source min and source max, and I will also increase the frequency, and let's set this to a simplex noise. All right, so now we can kind of see the pattern of our noise. Let's do on our bind export, we can export this to a density attribute. So let's maybe just disconnect the CD connection. I'll go up, and now if I go to the information, we have this density attribute. So from here we can do a volume rasterize attributes, and we can specify that the attribute we want to rasterize is going to be this density. So when I place this here, we can see our smoke, which is again based on our attribute. I will reduce the particle scale a little bit. Let's maybe use 0.1, or maybe, okay, let's just leave this at 0.15. It should be all right. And we will, and we can also adjust the voxel size, and we will tie this to our Pyrosolver voxel size. So in fact, from here, let's just plug this inside a Pyrosolver, and right away I will go in the setup, I will right click, copy parameter on the voxel size here, and we will paste relative references on our voxel size in the volume rasterize. So now if I'm in the Pyrosolver and I increase the resolution here, this will also increase the resolution on our volume rasterize attributes. So now we will use the same resolution on our sources as well, and this is what you usually want. Now back in our Pyrosolver, in our sourcing tab, Pyro already set up our usual suspects over here, so temperature, burn, velocity, and we see that we are also sourcing in the density. We are adding this as an operation, and if I press play, we see our density thickens, so we don't have any smoke rising because we don't have any of the other source volumes like temperature, burn and stuff like that. So let's go ahead and add those as well, and we can simply go in our attribute VOP. Maybe I can rename this to set attributes. We can step inside, and from over here we can also do another bind export from the same noise, and we can rename this to temperature. And if we remember from earlier, we want to offset the noises that we are using for the different sources. So in this case, it might be better if I just copy these nodes. I can grab these and duplicate these by holding Alt, and I will place this here. And then on our second noise, I will just increase the offset so we get a different pattern. But now we also have a temperature attribute, so if I go up, we have this temperature over here, and we will just have to add it to our list inside the volume rasterize. We can add here temperature as well. So now back in our Pyrosolver, we are already sourcing in the temperature. We can see the operation is set to pull by default, and if I press play, now our smoke rises as well. So we can do the same thing for our flame. Let's create this burn volume now. So let's go back inside. We'll just copy all of these, and I can offset this noise again, our third variation, and let's set the name here to burn. Okay, and if I go up, we'll just have to add this to our list, burn, and now we can see we also have our flame target field, and we have everything we need for a simulation. And it's the same if we want to source in velocities. We would just have to make sure that we have a velocity attribute on our point sources. So this is a more efficient way to create your sources rather than having everything as a separate source which you are then merging. You might still need to merge sources, so you might want to have some, maybe in the case for a velocity field, you might want to have this big container, so you can't really base it on the same geometry that the other sources are based on. So in that case, you will have to merge in different sources from different places. But a lot of the time for density, temperature and burn, these are usually based on the same geometry source. Now, with using the regular scatter mode, it's a little bit hard to tell how many points we need. So if I were to use less points over here, if I go now to the simulation, we have this result. So if I have less points, I would probably have to increase their scale in the volume rasterize. So if I increase the scale now, we might cover the surface that we need, but we have this ugly blocky look now, and we are changing the simulation, so we are not getting really consistent results. And because of this, Houdini added a special scatter node which is called the Pyro source. So I'll just copy the sphere over, and let's append a Pyro source node. Now, the default setup here, the default mode will be keep input, which will simply use the points that we have on our geometry. So if I go to the geometry and turn on point display, we have the same points on our scatter as well. This is not what you want to use in most cases. So let's set this to surface scatter instead. And now if I increase or decrease the particle separation, we scatter more points. There is also a volume scatter mode here if we want to scatter points inside the entire sphere, but usually it's enough if we just scatter points on the surface and this will be faster, so usually you want to use the surface scatter mode. So unlike the scatter where we directly set the point count, this particle separation kind of works like when we are working with volumes, meaning that as I decrease the particle separation, we actually increase the total point count. And the cool part about the Pyro source, we have a pre-built scale that is tied into the point count, which is this particle scale here set to a default of 2, and honestly you should just leave this as the default 2. If I go to the material icon over here and right click, I can set the particle display to be lit spheres, so we are also previewing the p-scale of the points, so we can see that as I increase this particle separation, so I scatter less points, our p-scale is adjusting accordingly to keep filling this gap. Whereas with the scatter, we don't have this dynamically resizing p-scale. So if I increase the total count here, we still have the same size on our sphere. And again, back in our Pyro source, we can see that the p-scale is adjusting to accommodate for the amount of points that we are using. And now we can also tie this particle separation to the resolution of our simulation. So in our Pyro solver, I'll go to the setup, I will right click, copy parameter on the voxel size, and I will set it to be the same as our particle separation. So let's use spaced relative references, and I can also just plug this inside our attribute VOP here, and we no longer need the scatter. So let's maybe readjust the nodes. So now our Pyro solver will have the same resolution as our sources and also as our particle separation here. So when I go to the Pyro solver and I decrease this voxel size, this will transfer over to the volume sources and also to the particle separation. So in this way, we will achieve the most consistent result when we are upgrading our resolution, so we can make tests on a smaller scale to find the right values. And then when we want to make our final simulation, and I set this to a lower scale, we will have a pretty consistent behavior in the simulation. And also in our volume rasterize attributes, this particle scale here is actually a multiplier of our existing value. So this should be set to 1 if we are using the Pyro source method. Now, this particle scale that our Pyro source gives us is pretty helpful, but a lot of the times I find that this dynamically readjusting of the particle scale might give us inconsistent results when we jump from a low resolution to a high resolution. So a lot of the times I still just prefer to use the scatter mode instead. I just make sure that I scatter enough points so that we have the complete coverage. And then in the volume rasterize attributes, just use or rather settle on a given scale here and then only worry about the resolution. So I found that this way we might actually get more consistent results when we change the resolutions of our Pyro solver. So it will be up to you to experiment. In our pro courses, we usually use the scatter method instead, but I wanted to cover the Pyro source node as well. Now, aside from the Pyro source, the Pyro burst source is a new addition. So let's drop this down. Let's type Pyro burst source and we'll drop this here. So this is a newer addition to the Pyro toolkit, and this really makes setting up sources super convenient. So if we play the animation, we just have a bunch of points that spawn and then expand and disappear really fast. So we see these only last for maybe 5 frames. And this is usually what we want for explosions. Let's maybe just set the display here back to points. But also on this note, if we set this to lit sphere, we can see that these points here have already randomized scale, which will help add noise in our sources. And all of these points have different colors, which correspond to a different attribute. So One color will be for density, one for temperature, and one for burn. We'll look at this in a second. But right away we can see that this node sets up a lot of stuff for us. So I'll just set this back to points to see this better. Now for a long while in Houdini we had to create these sources ourselves from scratch by combining different scatters on spheres with noises or doing pop simulations, and we can still create our sources from scratch, and that does come up a lot, but this node really speeds things up for us when setting up pyro effects. And with all of the default settings over here, we could simply source this directly inside a pyro solver. And if we just go to the components tab here, we see that we are already creating an attribute for the density and for the temperature and also our burn. And if I do from here, let's plug this inside the volume rasterize attributes and create our volumes. We want to rasterize our density, burn, and temperature, and also V, so velocity, which this node, or rather the pyro burst source, provides as well. So if I go to the point trail display, we can see our velocities over here. So we are going to rasterize those as well. So back in our volume rasterize, all of these default settings will be fine, but for coverage here, I'll remove the density attribute and leave this as an empty field. This means that all of the particles will receive the full coverage. And you can also think of coverage as influence. Now, when we are doing our own scatter, we don't usually have to worry too much about this. We can leave this at the default density, but the pyro burst source is set up in a specific way where there's no overlap between the density, burn, and temperature attributes. And also in the volume rasterize attributes, we should have this normally turned on, this normalized by clamp coverage. This is kind of like a filtering on the volumes, and in general it gives smoother results, as we can see. Now all this means over here is that if for some reason you're not seeing some of the volumes in your pyro simulation, so you might not get your burn volume to show up even though you are sourcing it in, make sure that this coverage attribute here is left as empty. So anyway, from here, let's reset the timeline, and I can just place this inside a pyro solver, and without doing any changes, just with the defaults, if I press play, we have a explosion. Now, this isn't looking too amazing, but we do have in fact everything we need to make this into a great looking explosion. From here, really, it's just a matter of adding noises to our sources and introducing microsolvers, and that's pretty much it. So if I go to the shape tab real quick, I can just introduce some disturbance. I'll set this to a high value. Let's also turn on turbulence. We want some flame expansion, so we do have our flame field, and we can just go to the fields tab, and in density and temperature, let's also emit from flame. And in the sourcing, we have all of the sources that we need, density, temperature, burn. Let's also do a divergence because we don't have this here by default. So we want to introduce a little bit more expansion right in the beginning. So I'll hit plus and I can base this. Let's grab our density and source this in divergence, and I'll just increase the scale here to 10. So just with these extra settings here, let's reset the simulation, and we can see we have a little bit more detail already. We can also do a ground collision. So in our collision tab, grounds plane, let's set the Y ground plane to close below and leave this at 0. So we'll also have some collision with our floor. So now it's starting to look more and more like an explosion. We can also go to the look tab and I can increase the density and maybe increase the shadow density as well, play around with some of these other settings, and maybe we can increase the disturbance. We can also introduce some shredding as well to noise up our simulation even more. And in the setup, maybe we can also decrease the voxel size. And because this is moving really fast, we can increase the maximum substeps to a value of 2 here. And let's take a look what we have now. So now it's really starting to look really cool and sort of like a real explosion. And we can see how fast this was to set up with our pyro burst source. So we can go over here back to our source, and we have a lot of options that we can play with here. Probably one of the more important ones is going to be in the output attributes. We want to add noise to our velocity. So if I turn this on and I look at the point trails, we can see that as I increase the amplitude, we add noise to our velocity. So this will further introduce more breakup in our velocity field, which is great. We can also introduce in our burst components, we can enable noise for the burn and also the temperature and maybe our density as well. And in the burst shape, let's maybe turn off point trail display. I want to increase maybe the number of trailings, or actually let's this trailing separation value is kind of the same thing that we discussed in our pyro source node, where we should link it to our voxel size. So here I will just copy the voxel size. Let's copy parameter. And of course, we would need the same voxel size in our volume rasterize. So let's paste relative references here. And also in our pyro burst source, we'll paste this for our trailing separation as well. So now we should have a more consistent look. So let's press play. Okay, so this is already starting to look better. I might want more divergence, but really at this point, it's just a matter of finessing all of the settings until you get the look that you're after. And in the Pyroburst source, we have a lot of different types that we can play around with. So we can do a shockwave, which is really cool, and it looks something like this. Let's again link the point separation with our voxel size, so it's 0.05. I might want to increase the initial size. Let's also add noise to this, and let's increase the amplitude here and maybe the roughness, and let's see what this will give us. So now we have this nice spreading shockwave kind of result. We can of course still play around with our sourcing, so maybe in our velocity advection here I can increase the source scale. So let's maybe set this to a value of 3, and now our fire will get pushed out a lot further. So in this case, for a shockwave, this might be a better look. So we can see now the different results. Now we know what all of the different microsolvers do and what the sourcing does and the types of operations that we have, but really these are a lot of things for us to remember, and as beginners it's going to be impossible to remember everything we need just from a few tries. And this is why Houdini has a lot of examples for us to use and explore. So if I type here pyro configure, we have a lot of different pre-built setups that we can use. So if I drop down a pyro configure fireball, let's drop this here, we can see it automatically created a chain for us with everything we need and all of the settings that we need. So if I press play and see what this looks like, here we have an explosion that works right from the start. So we have all of the right settings in all of the nodes, including the pyro burst source, our volume rasterize, and of course our pyro solver. So we can see we can increase the resolution here. So I might want to bump up the quality a little bit. Let's try 0.05. And now this is starting to look really great. And you can imagine that if we actually render this and add some glow on top, this will serve as a very nice and believable explosion. So if we check all of the settings that Houdini set up for us, we can see in the bounce tab, for example, everything that is highlighted is changed. So they increase the padding here from the default. If I reset this with control and middle mouse click, we see that the default is 0.3. So they set this to 1 because this is a fast moving smoke, and this echoes back to what we talked about earlier when we talked about padding. Then we have the collision with the ground plane set over here. In the sourcing, we have all of the different sourcing. We can see, for example, they sourced the burn inside the divergence, and we usually use density, but the burn can be just as good in this case with a source scale of 10. All the different settings for velocity, for example, and in the fields tab we have emit from flame for temperature and density, and in the shape tab we have a lot of stuff, and we even see that they animated the turbulence. So if I shift click on this value here, the turbulence starts out really high in the beginning. So if I reset the timeline, we have a, let's take a look, this is using an expression, don't worry about this. So they have a turbulence of 5, and over a period of I believe 12 frames they are scaling this back down to maybe a lower value, and this is to add a lot of turbulence as the simulation, or rather the explosion, starts to break up the shapes in order to create all the interesting features, and then it slowly settles to a low value as the explosion slows down. And we can even see on the pyrobake volume the way this is set up by using the scatter field, which by default has a binding on temperature and density. So if we go to the scatter here, we can play around with some of the settings, but Houdini already gave us a pretty good starting point. So at any point as you are working on your own simulations, you can always drop down a Pyro configure something and check out how they set it up to know at least in the ballpark what kind of values you should be using. And there's really a lot of options to explore. So again, if I type, let's do configure pyro, we see there's bonfire, fireball, shockwave, aerial explosion. All of these are really, really good examples that you should spend a little bit of time just going through all of the different settings and trying different settings yourself. And if you want from here, you can look at our Dragon Fire Breath course, which is a free follow-along tutorial where we created a cool fire-breathing dragon shot to further expand on your pyro knowledge. So hopefully this course helped, and I hope now you'll be confident to jump into pyro simulations. I really like pyro. I think it's one of the most fun solvers, and definitely let me know what you think. So until we meet again, keep on simulating, and I'll see you next time.